Well, maybe we'll go ahead and start. First, let me remind you where we are. So I'm going to finish off sort of at a very high level, just a few more examples. One I can go very quickly over because it's machine learning. And then I know I got a couple of mild but polite complaints that there wasn't enough math yesterday. There will be math today. So actually, I'm curious how many people actually did the homework. I thought so. So, okay. So, just so you know, the people who take this class at Stanford, and there are a lot of them, a lot more than you, they actually do all the homework and stuff like that. They actually learn stuff instead of just learning about words and things like that. They can actually do stuff. So, okay. You can do the homework if you want. Okay, so the next example, simple is just control. It's a very simple thing. It's this. You have a linear dynamical system here. So you have a state, which is a vector xt, and it propagates. It's affine in both the previous state, that's the next state, is affine function, a linear function actually, of the previous state, and the input u. So u is something like inputs or actions, and this model, this dynamical model, will actually describe an enormous number of practical applications, right? It describes essentially all of control, like chemical process, vehicle control, guidance, things like that. It also, by the way, gives filtering, but that's another story, dynamic system filtering. Yeah. Yes, I can. Yeah. So is it a signal to noise? I can certainly speak up. So is that okay? Because it could be a signal to noise ratio with the fan. Would you rather? No, that's all right. Okay. You want the fan on? Yeah, I do too. Okay, I'll speak up. So just wave your hands if I don't speak up enough. Great. Okay. But it also describes things like supply chain systems, right? So where xt is your vector of the amount of different multiple products you have at different places. Ut is how much you ship from one place to another, how much you consume, how much you pull out of the supply chain, how much you put in, right? So this describes many systems. Okay. You have a stage cost for, which is a function of the state and the action. And you have a terminal cost. You're going to run this out capital T periods or time steps. And you'll have like a final state constraint, and you have state action constraints and so on. So when these cost functions are convex and these sets are convex, that's a convex optimization problem, right? So that's, this is just generically control. Let's look at a quick example. You have a system with, let's say, 8 states, 2 inputs, horizon of 50 steps. You choose some random data, random but reasonable, interesting data. The constraint is that the inputs are limited by plus minus 1, all of them, right? So, and you have a terminal constraint. The terminal constraint is xt is 0. That's called a regulator. By the way, part of this is also for you to learn about other problems if you haven't seen them before, right? So, regulator, typically in a regulator, the state is deviation from some desired state, right? So if you have an airplane, it's deviation from what your current like commanded cruise is, like, you know, whatever it is, 485 knots at, you know, 32,000 feet. That's x equals 0, right? And so anything away. So this says that at the end of that thing, you must be in your commanded state. And then we use a very traditional, this goes back now 50 years, a traditional quadratic cost. And the inputs look something like this. You can see that they're slammed up against the limits much of the time, not all the time, but much of the time. And then this would show you what the actual state trajectory is. The point here is that actually these are not obvious. This is beyond anything a human being can do. Right, so, I mean, a pilot can do this. They'll do actually a rather crappy job compared to what you can do. So what something like this will do. So this is the idea. But this is a convex problem. I should also mention that there's a lot of sort of theory about this. You can take a whole class on control theory and hear about the Pontryagin maximum principle, all these kinds of things. It's very interesting and totally useless. Unless you have like a baby problem with like 2 states or something like that, right? So, okay. And the last one, I think I can go pretty quickly over because I presume everybody here knows all about this, is we'll just look at something like a support. This is just an example of what you can do. And you can, for example, do a support vector machine with L1 regularization. So what you do is you're given data, which are pairs. It's a feature vector, and then a Boolean outcome. And what you're going to make you're going to choose coefficients in a linear classifier. So you're going to choose a vector beta and an offset v. And you want to find these parameters. And you're going to do that by minimizing this convex function, right? So, by the way, we're not doing it by writing out slacks and things like that. You're going to see later today why that's actually a bit childish and stuff. You don't need to do that. That stuff like that is actually all done for you. And frankly, this is far clearer, right? So what you want, of course, is you would like on your data, that should be an I there, by the way. That's a mistake. But in your data, what you'd like is you'd like this and this to have the same sign, right? So the product should be positive, right? And in fact, but the whole thing is homogeneous, so you're going to have a margin, and the margin's going to be 1. And so what you're saying is you really want the product here to be bigger than 1. As long as it's bigger than 0, you've made the right decision. But bigger than 1 is bigger with your margin, right? So I don't know if this is how you had SVM explained to you, but this is how I think of it. And so this cost function says that once this thing is bigger than 1, you charge nothing for it. This is the positive part. You start charging as soon as you're less than your margin, and you charge linearly. By the way, if this cost here goes above 1, it means actually on that example, you made the wrong classification, right? So, okay. So this is the average loss or classification error or something like that. And then to this, you add, at the same time, you'd like beta small. And we're going to say beta is small in L1 norm. And that's going to do two things. It's going to shrink beta, and it's also going to encourage sparsity in beta. Okay? So, all right. So this will simultaneously select the features, and it'll fit the classifier, right? So that's the idea. And here would just be a very baby quick example just to see how this works. You just generate some data from a simple model, and then you train and test it, and these would be the train and the test errors, right? And they're similar, and that tells you that you are not overfit. And here you'd find out that your best precision is somewhere at around this value. I guess that's 0.3 or something like that, right? And then this, if you haven't seen these before, but actually I'm presuming everyone has seen something like this. Has everyone seen a plot like this? A regularization path? Is that like absolutely everyone or almost everyone? Okay, so if you haven't, it's at least one person who hasn't, so probably more. This is worth seeing, right? So we chose a small number of features so we could actually plot them all. So there's 20 things here. And what happens is you crank up lambda, what will happen is these features will actually extinguish. They'll become 0. Actually, there are some cases where a feature will actually become 0, and as you increase lambda, they'll actually become non-zero again. So it's not monotonic. And here, the best example here turned out around here, which is 0.3. And if we go down to this plot, at that point, we have 1, 2, 3, 4 out of the 20 features are non-zero. So you've selected 4 features and you've set the weights and so on, right? So this is the idea. So again, these are just simple examples. These are just very simple examples of convex optimization. Okay, I'll finish this up. This is part of the first lecture, but I'll finish that up now. And so the summary is something like this: convex optimization, they arise in a lot of applications, right? So that's the main point. You'll see a whole lot more before tomorrow is over. And they can be solved effectively. Generic problems, if you have things that are not huge, right? So if you have, a problem with, 10,000 or 50,000 variables, if there's enough sparsity in the problem or some other structure, these are just readily solved using generic methods, right? If you really have a big, huge problem, then you can develop custom methods for them, right? And people are doing that. An important part, which I guess most people don't, it depends on your cultural background and what, the groups you move in. But what a lot of people don't really know, some people don't know about and others don't appreciate enough, is the idea that these high-level languages actually support the formulation and solving of these things very, very quickly, right? So that's actually what today is going to be about. Half of today is going to be about that. So the idea is that roughly speaking, once a problem is known to be convex, you can at least get something that will solve it if it's not huge pretty quickly, right? So that's the idea. Okay. Resources, there's lots. I mean, this is what Google is for, so you don't need anything. There's only one thing I do want to say, and that is that the topics I covered it's critically important you understand these were done by hundreds and hundreds of people, right? And certainly not my group, and certainly not me. So please don't come and say, oh, your methods or something like that, because It upsets me. So, okay. So what we're going to do today, now, is we're going to actually get into some of the mathematical details. And it's going to be a bit of a strange, it's going to be strange, because it's not going to be the standard one. It's going to be a weird one. We'll see what it is. But we're going to go through, I'm going to teach you enough convex analysis so that you can actually be minimally competent, right? And then what you'll see is that along with that convex analysis, there's software support that goes with it, and that'll actually make you actually be able to do stuff. So I'll do a whirlwind overview of convex optimization. I think I'll make that very fast because we covered that last lecture. And then what we'll do is we'll talk about constructive convex analysis. That's going to be math. And then we're going to look at the software implementation of that. That would be something like disciplined convex programming. That's actually not software, but you'll see what it is. We'll talk about some modeling frameworks, and then I'll wrap up for today. So, okay. So this is generic, and you've seen this before. I mean, just to remind you, this is what a convex optimization problem looks like, right? You minimize an objective, you have inequality constraints. The objective function and the inequality constraint functions are convex, right? So that's the idea. And the equality constraints are linear, okay? So that's a convex optimization problem. And what I want to mention now is the idea of the conic form, right? So this has actually emerged as sort of a standard form for convex optimization problems. It emerged maybe in the last 15 years, 10 years, 5 years, whatever, something like that. It looks very specialized. So let me show you what it looks like. You minimize, well, it's a convex function, but it's a very specific one. You minimize a linear function subject to, well, here are your equality constraints. That's not different. All nonlinearity in the objective and all constraints is shoved into a constraint that says that this variable lies in a cone, a convex cone. So that's the idea. So this is a so-called conic form. It looks very specialized. We'll see that it's not. It's actually completely general, but it looks specialized. Now here, the idea, I mean, one idea behind this is the following, is if this was the cone of non-negative vectors, right, then this would be a standard form linear program, and it would be recognizable by people in 1948. Okay? So that's the idea. So, and in fact, one of the advantages of this form, I mean, there are several advantages, but one advantage is that actually, for people in OR, if you do operations research or optimization and you do the classical stuff, then this is very familiar to you because it's just like linear programming, which is very close to you, which is very, it's something you learned when you were young and all that kind of stuff. So this makes you very comfortable. And the only thing you're saying is I'm going to swap out your non-negative cone, the concept of non-negativity, and replace it with a different concept of non-negativity. So for example, if x, the vector, is an encoding of a symmetric matrix, then I could make this cone the cone of positive semi-definite matrices. And then this would be a so-called semi-definite program. And now we're up to modern times, right? So this would be sort of something that people talk about a lot. Okay. Now, it turns out, here's the weird part. You'll never see this again, at least in this short course, because you don't need to. But let me tell you what this is. Here are the things you need to know about it. There are very well-developed solvers for cone programs to solve this. So, and then someone was sitting around here, kept asking me how. So, someone should ask. Why don't you ask me, how do you solve cone programs? None of your goddamn business. Okay, so I just wanted to say that again. So, thank you. For asking the question. Okay, the honest truth is, so first of all, as a zero-level response, that was the correct response. It's none of your business. There are many ways to solve them, right? And some have nice theoretical guarantees, some actually work in practice. These are not necessarily the same groups. Some scale to extremely large problems, but deliver only modest accuracy. Others work unbelievably well with low variance in runtime if they're small enough, and so on. So there's tons and tons of different cone solvers, and it's kind of what people do. If you really work on high-end convex optimization, you work on developing cone solvers. And then a cone solver will depend on what types of cones. This is generally a Cartesian products of cones, and it'll depend different cone solvers support different kinds of cones, right? The simplest one would be, this is just R plus to the n, in which case that's called a linear programming solver, and there's a gazillion of them, right? Then there would be a second order cone programming solver, you know, and there's many others that do this kind of thing. Okay, same SDP solver. Okay. The other thing is that this is really, what this has emerged as is essentially the intermediate form, and I mean that in a computer science point of view, right? So when you have a compiler and you write something in a high-level language, the first thing your compiler does is it translates it down to some intermediate form. And it's an intermediate representation of some abstract machine, or maybe less than abstract machine, right? It's not runnable yet, but it's a standard intermediate form, and then other people work on building the runtime, either the thing that generates the final runtime machine code, or they run the thing that actually runs the intermediate code. So this should be, you should think of this, I actually think it's a very good idea. This is the intermediate form, the 3-byte code, whatever you want to call it, for convex optimization is this, right? And so you should look at it about as often as you look at the intermediate form that comes out of a compiler, which is never, okay? So, but it's good to know that it's here. So, okay. So we talked about this yesterday, so I'm going to go super fast, right? So why convex optimization? Well, because basically it corresponds to the things you can actually do. Oh, by the way, if you're welcome to actually not solve a problem, if that's okay with you, then you shouldn't worry about convexity. By the way, I should also say that that's unbelievably useful, right? If somebody comes along, has a problem, it's not convex, and they can run an algorithm and your revenue goes up, right? Or your hedge fund is doing well, then you probably are not going to be consumed at night with worries that you haven't found a global solution. You see what I'm saying? Right. By the way, if you're doing worst case analysis, that's maybe another story. Then maybe you will stay up at night, right? Or if you're in a very competitive industry where you've heard some other competing firm is actually going to convexify the problem, then you might want to worry, right? But generally, there are lots of cases where if you don't care, this is just fine. All right. So what's nice about it, I mean, the summary is basically that there's solution elements that work well in theory and practice. But what this, I think for me, what this is means it's, of course, this is math, right? But what's actually nice about it is it's actionable math. So what I mean is you don't just sit around and say, oh, you know, this has, I can prove, what would be the worst thing would be, let me pick on it, economics, right? So the unbelievable. You could say, oh well, you know, by some Schauder fixed point theorem, it means there's an equilibrium, right? Well, that's completely non-actionable. Not to mention means nothing, right? So it doesn't mean you can do anything, right? Because if you have a fixed point problem that depends on one of these Schauder-Brouwer fixed point theorems, the only algorithms to solve these are exponential, and anyway, they're very sensitive, so it's not something that has any consequence. It's very interesting mathematically, has zero consequences, zero in real life, right? These have consequences, right? And they're actionable. It means you can actually do it. So, okay. So now we're going to start. So the question is, how do you solve one? And again, I'm only going to talk about how you solve one. I will not tell you how to solve one. Although later I'll probably ask you again to ask me how to solve it. So just to remind you what the point is here, right? So you can use an existing custom solver for your specific problem. If you want to solve something that zillions of other people are doing, like let's say L1 regularized logistic regression. Okay, fine. So why would you not use something in some package in R or GLMnet or whatever it is, right? I mean, go ahead. I mean, of course you should, right? Because that's been tuned for that problem, and why would you not? Okay. Now, you could also develop a new solver for your problem, right? And then that allows you to show off, because you could use whatever is the most, you go to NIPS or whatever and look at the most fashionable, you go to archive, do some machine learning on it to find out what terms people are using, what's trending, you make a prediction, and then you put those adjectives into your algorithm and make a thing, and then make a proof that's too long so no one even knows if it's a proof. Voila. Okay, everybody got that? That was fast, but I think everyone here understands what I'm saying. So, okay, fine. Now that requires work. Now the payoff of that, of course, is that you actually can scale to large problems, right? I mean, because it could also be customized for your platform too, right? So you could do this on, Spark or something like that. Okay. We're going to talk about something else that's a very interesting method. I think, as far as I know, it's been used approximately zero. This is actually the only way people do this. Actually, these first two are what people use in machine learning. That's what they do. right? So, which is fine, nothing wrong with that. The third method is interesting, general method. What you're going to do is you're going to take the problem and you're going to transform it into a cone program. This is like compiling high-level source into some intermediate form, and then you're going to let a runtime engine or something like that execute it, right? So that's the idea. And the point is, this is going to be automated using domain-specific languages. So that's going to be the idea. And it's going to go along with the math as well. So that's the idea. And this is what we're going to talk about, right? So, okay. So now we're going to do some math. It's a whirlwind tour. I'll go a bit slow. I mean, we'll see, not slow, but we're going to cover a lot of material. But actually, it won't take very long. But when you put the pieces together, you'll actually know a lot. So we'll just start. Everything's going to come down to figuring out whether a function is convex, concave, or both. If it's both, that means it's affine. Okay? Affine is easy to detect, right? It means it's a linear function plus a constant, right? So this is convex, that's concave, and this is affine. Okay. So you say that a function is concave if it's negative is convex, which means it satisfies this inequality. It's affine if it satisfies this inequality for any theta between 0 and 1, but it could be any. And it's convex, of course, if it satisfies this inequality with the inequality going the other direction. So these are the two. So this we call the curvature of a function, right? So, and in fact, there's essentially 4 curvatures, which are, well, it's even simpler than that, but there's 4 curvatures. There's convex, concave, affine, which is both, and then neither, right? And I think we had a famous example yesterday, the sine. Sine is like neither convex nor concave, okay? Most functions, of course, are neither convex nor concave. Okay. Well, how do you check if a function is convex or concave? Okay, so the first thing I should say is if it's a function of a single variable, it's super duper easy. This is how you do it. You plot it, and you look at it, and you use your eyeball. That's how you do it. If it curves upwards, it's convex. If it curves downwards, it's concave. If it curves sometimes up, sometimes down, it's neither. Okay? I didn't do that. Okay. So that's how you do it for a function of one variable. Right, but by the way, after that, then you make some fancy proof that's 3 lines, right? But the truth is you did it first by just plotting it, okay? And this will even work for functions of 2 variables too, I guess, right, or something. Okay, so how do you prove a function is convex or concave? Well, you could apply the basic definition. You could say let x and y be any 2 points in the domain, let theta be any number between 0 and 1, and then you check if the inequality holds, and you do your normal, what you're trained to do, your math, right? So you can do that. Yeah, that'll work for like 2 or 3 different things, very simple things. You could do it by first or second order conditions. For example, if a function has 2 derivatives, you could form the Hessian, and then you could try to verify that the Hessian is everywhere positive semi-definite, right? That of course makes sense. This is the standard, second order condition for convexity. And so this would be one way to do it. And again, this will work for some very simple f's, but beyond that, this is a giant headache and not a good way to go. Now, the correct way to do it is this, is via convex calculus. So the way that's going to work is this. You're going to construct f using a function, using a library of basic functions that are convex or concave. I'm going to show you some shortly. Right? So you have a basic library. You understand, you memorize or whatever, 10, 15, 20 things. No more than that. You don't need any more than that. Right? 10, 15 things. And most of them are kind of obvious anyway. Some are not obvious. You're going to see some that are obvious, some not obvious. So you just memorize those, that's fine. And then you're going to have a set of calculus rules or transformations that preserve convexity, okay? Most of these are going to be very obvious. A few are not going to be obvious, okay? So that's how it's going to work. And we're also going to find out, it's even cooler than that, because mathematically, it's going to come down to there's only one rule. So, but we'll get to that. Okay, so let's start with some simple things. Here's some. Well, x squared, there you go, or x to the 3 halves. That's defined, of course, for x positive, the 3 halves, right? So that's going to be, you just look at this picture in your mind, what the plot is. It goes up, it's convex, okay? Curves up. 1 over x is convex. 1 over square root x, these are convex because they look like this, right? They go down like that, right? Oh, the domain is x positive here, right? So you do have to be careful about domains here. All right. Exponential, differentiate it, and it's non-negative, twice, in which case you get e to the x back, and it's non-negative, so done. or you just look at it, right? Negative entropy, right? So that's the negative entropy is convex. That means, of course, that entropy is concave, right? So, by the way, that's good, because remember, roughly speaking, we can minimize convex functions and we can maximize concave functions. And that says that when you hear the term maximum entropy, they play nice algorithmically, right? That's what you want to hear. You want to hear like minimum distance, minimum loss. You want those things to be convex functions. If you want to maximize something like entropy, maximum entropy, that plays nice. Okay. Okay. Things like here, an affine function. That's an affine function on Rn. Well, of course, it's affine, right? So it's convex. It's also concave, right? It's basically a function. It's got zero curvature, right? It's flat. It's actually on the boundary line between convex and concave functions, right? Quadratics. This is good to know. If you have a quadratic form, it's going to be convex if and only if the matrix is positive semi-definite. The Hessian is 2p, so this makes sense. Okay. Well, for that matter, any norm is convex. That comes from the properties of a norm, so homogeneity and the triangle inequality, right? So these are all convex. Here's one, maybe not so obvious, but the max of n, the max function, right? So this is a piecewise linear function, right? So, and it's going to be convex. It's not hard to show. It's like 2 lines, okay? And it kind of makes sense that it would be convex, right? Well, you can certainly imagine what it looks like if there's 2 variables, right? You have max of x1 and x2 in a plane, and you imagine what it looks like, and it looks like it's got a line down the middle, right, when x1 equals x2, and then it goes up like this on either side, right? So that's going to be convex. Yeah, these are basic ones. Here are some basic concave functions. And these are things you just simply have to know these. Actually, there's no reason not to know these things. These are incredibly basic. If you do any math at all, you need to know these things because it's not just for doing convex optimization, but for making inequalities. If you ever want to make an inequality and you don't know about convex analysis, you are hobbled, right? Basically, there are people who claim essentially all known inequalities. I mean, it's not quite true, but all known inequalities come from basically convex analysis, applying a Jensen inequality to some appropriate convex function. So that's actually pretty much true. So, okay, so here are some basic ones. X to the 0.3 or square root x, right? That would be, so for powers between 0 and 1, these are going to be concave. The log, well, of course, I mean, the log goes up like this, right? Geometric mean, that's maybe not so obvious, but you know the arithmetic geometric mean inequality, and that is a hint that this inequality, that this thing is going to be concave. This is easy enough. I mean, you could write out the Hessian. It's a 2x2 matrix, and you check that it's positive. It's negative. Actually, it's negative semi-definite. Okay, so you check that. Quadratic function with a negative semi-definite coefficient matrix, and the min. So the minimum of concave function. Well, the minimum of a set of variables is concave. Okay. Now we're going to look at some less basic ones. These are not obvious. But this is just because otherwise this is not interesting. A lot of these are actually very useful. Here's the simplest function there is that most people don't know is convex. And this is very much worth knowing. It's 2 variables, x squared over y, and it's restricted to y positive. And that's jointly convex in x and y. That is not obvious. Okay? It has huge numbers of implications in essentially every field, but especially in statistics, right? So you may know it by some other name, or you know consequences of it, but trust me, this is an important thing to know, right? So actually what this is sort of like a least squares cost with also the weight, the inverse of the weight. And it turns out that's jointly convex in both the argument and the inverse weight. And this is already interesting. So here it is, it's x squared over y. By the way, what's clear here is if I fix a positive y, that's convex in x, because it's just this. If I fix x and I look in y, it's convex in, if I fix x and vary y, it's clearly convex in y because it looks like this, right? By the way, that's of course not good enough to say that it's jointly convex, right? So, but it is. There's variations on this. Sum of squares divided by y, that's convex. We'll get to why that is. It's kind of obvious. Here's one that's not obvious at all. If my variables are a positive definite matrix and a vector x, so positive definite matrix y and a vector x, this thing, which is x transpose y inverse x, that's jointly convex in both x and capital Y. That is not obvious, just in case you think it is. I mean, I can make a 3-line proof, but that doesn't mean it was obvious. Okay? So, I mean, these are already getting very close to things that are, that are close to you. These are things. If you put in here something like, there's all sorts of examples from statistics where it just goes on and on and on. So anyway, these are not obvious, right? So this says, by the way, if I take like x, y, a pair, and I take another pair, x tilde, y tilde, and if I, for example, create the average of the two, so x plus x tilde over 2, y plus y tilde over 2, and I compute that number, it'll be less than the average for that composite one. It'll be less than the average at the endpoint. That's the basic inequality. Okay. Here's another function, the log of the sum of of exponentials, right? So you probably have seen this somewhere. It comes up if you've done any kind of applied math in any application area, you will have seen this. Different fields have different names for this. Some people call this a soft max because that's what it is. If you think about it, if one of the x's is much larger than the others, then e to that x is much, much bigger. And then basically you take the log and it's basically very close to the max, right? So this is an analytic function which is the max, right? It's going to come up later when we do probabilistic stuff. Somebody asked about what happens when functions are random. We'll get to that later. Okay, so this comes up in electrical engineering. It's standard. It's how you combine powers from incoherent sources, right? Powers expressed in decibels, which is that's EE dialect for the log of a power. Okay, so this is log sum exp. Well, here, if I just take one of these to be, if I take x1 to be 0 and x2 to be x2, then this is the logistic loss function, right? So this is logistic loss. So no one here can claim they haven't seen this. Okay. Here's one. If I take the function of a variable x, which is the sum of the k largest entries in a vector, okay? It's a piecewise linear function, right? So the sum of the 5 largest entries in a vector, piecewise linear function of a vector, and it's convex. That is not obvious, right? By the way, to show this, I mean, you'd have all sorts of disasters, right? Here, what happens if we take the second, what if you take the Hessian of this? What's the Hessian of that? Well, what's the Hessian?
I don't think it's real. Can you derive it?
What?
I don't think you can derive it.
You can't derive, why can you not derive it? That's true, you cannot derive it.
It's not continuous, it's not smooth.
It's not smooth, yeah, because, well, let's be more precise. You can't find the second derivative of it because it's not second differentiable. Yeah. Right, okay, yeah, so that's the right way to say it. But notice I said it didn't, okay. So that's, yeah. So no, you can't do it. The Hessian is actually 0 at almost all points. And then, of course, it doesn't exist actually it doesn't exist whenever actually the kth and the k plus 1th entries are equal. This thing it's not differentiable, let alone twice differentiable, okay? So we're going to see that this comes up interesting ways. But it's an interesting function because if k is 1, it's actually the largest, so it's the maximum, and we already knew that was convex. Okay? If k equals n, it's the sum, but the sum is convex because it's a linear function, right? So this says, though, that the sum of the top 5 entries is going to be convex. Here's one, x log x over y, with x and y positive. And this is related to things like Bregman divergence, KL divergence, all these kinds of things. So you can derive everything you need to know from there. Actually, you'll get much more sophisticated functions than the ones you're used to, because you'll get the ones which are extensions into Rn and not just on the probability simplex. Okay, but we'll see that. Okay, here's one. The maximum eigenvalue of a symmetric matrix. That's going to be convex. Okay, so by the way, that's an incredibly complicated function, right? It's yeah, how do you find it? You take the matrix X. In theory, this is what you do. You take the matrix X, you form the characteristic polynomial. You take the characteristic polynomial, you factor it. Oh, oops, there's no formula for that if n is bigger than or equal to 5, right? Then, again, if you take this thing, and then you then you look at all the roots. They're all going to be real, and then you take the largest of those, right? So it's not remotely obvious that these things are that this is convex, right? In particular, there's no formula for that if x is bigger than 5 by 5. If 5 by 5 or bigger, okay? Everybody know what I'm talking about? I have to recalibrate. I'm going to take that as a, no. Yeah, so you can't factor, there's no closed form formula for a polynomial of degree 5 or bigger. That's what it is, right, so. Okay. Okay, so here are some concave functions that are less obvious, right? Here's one, very important, entropy of a Gaussian random variable, that's log det x, right? So you take a positive definite matrix, you take the log of the determinant, that's a very complicated function, it's concave, okay? Already notice that everything is starting to, things work out, they're not symmetric, right? So of course, that's the entropy of a Gaussian random variable with covariance x, right? So, and this says concave, that says we can maximize it. Oh, maximum entropy, that's something we'd like, okay? So here's one, log of a Gaussian, of a CDF, right? So you can just work this out. I mean, here it is in your, looks like this, looks like that, right? Then you take the log, and it looks like this. It goes like this, and then it goes down like that, okay? It actually goes down kind of quadratically, right? So it's, that's one. And again, this is not obvious. Of course, it's a function of one variable. So I mean, for God's sakes, you can take the derivative and check, right? The second derivative and check. It's not even that easy to prove it, right? So, but you can do it. Minimum eigenvalue of a symmetric matrix. Okay, so actually, this number is already enough. This is more than the atoms you actually need to know, right? So, okay. Now I'm going to tell you about the calculus rules. So some are totally obvious. Here's one. If you have a function, that's convex, then 2.1 times it is convex. That's obvious, right? Because if it curves up and you multiply by 2.1, it still curves up. Okay? That wasn't a proof, of course, but actually it's close enough, right? Okay. So here's one. You can add two convex functions and you get something that's convex. It's kind of obvious, right? These all are 1-2 line things, right? Okay. Affine composition. So if I have a function, and if I precompose it with an affine function, that's going to be convex. Why? Because if I have like x and y and some theta, and I form theta x plus 1 minus theta y, and I put this through here, it's the same as theta times ax plus b, plus 1 minus theta times ay plus b. Okay, so that just passes right through. Okay, so these are really odd. Here's one. The pointwise maximum of convex functions is convex. Okay, and again, this is kind of obvious. Just picture something that goes like this, right? Pictures something that goes like that. The same thing maybe shifted a bit to the right, and the maximum is the thing that goes down and then up again, and it'll have a point, right? So it's also a one-liner to show that the maximum of convex functions is convex. By the way, this one is interesting because this one here introduces non-differentiability, right? So if I have the max of x squared and the max of x minus 1 quantity squared, that's going to be, it's going to have a sharp point there. So it's not differentiable. Okay. And composition. So here's one. A convex increasing function of a convex function is convex. Okay? So the exp of a convex function is convex. The positive part of a convex function is convex. Okay? Because the positive part is the function that's 0. And then when you hit 0, it starts ramping up linearly. That itself is a convex function, and it's increasing. Everybody got this? So here are your calculus rules. Okay. Now, there's similar rules for concave functions, right? So just replace convex with concave here. This one, you switch max into min. And here, composition, it's the same thing, except that here, h is concave. A concave increasing function of a concave function is concave. Okay? So that's it. All right. There's going to be some cool things. So, okay. So these are all pretty simple. These are not hard to show. But it turns out you already know a lot just fiddling around. So here's one. Let's take a piecewise, this is a general piecewise linear convex function. It's the maximum of a bunch of affine functions. Okay? So that's going to be convex, right? Again, you know, taking out your, working out the Hessian is totally useless because it doesn't have a Hessian at some points, right? So here's your function. And what we'll do is, let's actually show this. Well, each of these functions, AI transpose x plus bi, is affine. But affine is a special case of convex. So these functions are convex. And now, let's go to the previous, and let's use our calculus rule. The calculus rule says that if I have some convex functions, their max is convex. And so here, again, the idea is, what we did was these are they're affine functions, which are therefore convex. They're also concave. And it says that this thing matched our third rule, right? And therefore it's convex. Okay? Here's one. How about the lasso, or L1 regularized least squares cost, right? So we have a variable x. We have ax minus b. That's and we take the sum of the squares of that. So that's your classical, you know, whatever it is, regression, quadratic regression loss function or whatever. That's this thing. That is convex there are many ways to see it. One way would be to write this out as x transpose A x, and then observe that A transpose A is positive semi-definite. Here's another way that uses other rules. Another rule would be to look at this and say ax minus b is affine. The norm squared is the sum of squares. That's a convex function. So this is a convex function of an affine function. That's convex. I mean, after a while you look at this and it's totally obvious, right? So I guess in the Stanford course, for the first couple of weeks, we insist that people say exactly why something is convex. And then, you know, as the course goes on, you wouldn't even say it. You just say that's convex because it's expected that you've internalized all these rules and you know instantly what is and what isn't, right? So, okay. Let's go on. That's a norm, so that's convex. Now I use the rule that says I multiply a convex function with a non-negative parameter, constant, and it says that that function is convex. Well, sure. And then I'm going to use the rule that the sum of two convex functions is convex. So I don't know if you're following this, but if you know undergraduate computer science, we've actually made the parse tree of that expression, and we're actually walking the tree. And we're actually checking that at each node, it matches one of our rules. Everybody got this? So I'm just hinting at what's to come. Okay. How about the sum of the largest k entries of x? That is not obvious to show. So, any suggestions about? I claim it's such a short proof that I can say it in words and it'll be totally clear, and we don't even have to raise the board. Any suggestions using what we know?
It's the sum of the maximum function.
Mm-hmm. Of what?
We're getting the maximum k elements of a vector and summing them up. So there is
I'm not going for it. No, it's very close, but I'm not going. No, I don't. No, this is very close. Yeah.
Could you look at all possible sums with only k elements?
I like that one. That was I think that's what you were trying to say. That's it.
And take the maximum?
That's right. So here's what you do. You take an n vector, and you look at all n choose k vectors, A, which have exactly k ones and n minus k zeros. You form A transpose x. That's a linear function, and it's the sum of a particular choice of 5 entries in the vector. Everybody got that? Those are linear. And now we're going to take the maximum over n choose k linear functions, and the way to maximize that is to line up, it's exactly what you said, you line up those things with the largest 5. Everybody get that? I mean, it doesn't matter if you didn't, but the point, all I want to say is we've actually done something now, and if you were to internalize the rules you've seen, on the atoms you've seen and the rules you've seen, you already know much more than you think, like a lot. Okay, let's do KL divergence, right? By the way, this is not KL divergence between two probability distributions. It's KL divergence between two non-negative vectors, which is more sophisticated, right? So it's extended to the entire non-negative orthon. So let's look at that. We would start, I mean, there's lots and lots of ways to show this. Actually, that's one of our atoms. I think we showed that U log u over v is going to be concave. That's the simple one. By the way, that one is so simple it's within striking distance if you just take the Hessian and get it over with. Okay? So that's what you do. So these are concave functions. Now let's see, each of these, those are all linear functions of the variables u and v. Okay, so these are linear functions of u and v, and therefore they're also concave. So by the way, back to undergraduate computer science, we're automatically recasting or promoting affine functions to be convex or concave depending on which is useful for us. In this case, we're noting that these are actually concave functions. I mean, well, okay, minus u is concave and plus v is concave, and now I'm saying I'm adding concave functions. Everybody got that? Sum of concave is concave. Done. Okay? So this is the idea. By the way, you might not even know this, right? Because what most people would normally see, sorry, this convex. I was saying concave, I meant convex, sorry. Most people would know that this would be convex in one or the other, not both. Okay? So, but it is, in fact, concave in both. Okay. So now it turns out, let's go back and look at our composition rules, right? So here's our composition rules. It was non-negative scaling, it's sum, affine precomposition, pointwise maximum, and then a composition, right? So, so when you teach human beings, these are good rules because they're simple, they're obvious. Most of them are pretty obvious. There's not one of these takes more than 3 lines to show or something like that, right? But it turns out these all follow from one. There's actually only one rule. And it turns out there's only one you need to know. So it's this. The rule is very, very simple, but it's not one many people know. So unless you do this kind of thing. So here it is. It's vector composition. It says if I have a function which is a composition of a function of k variables, that's h, of f1 of x up through fk of this, then this thing is convex if h is convex, if the calling function is convex, and the following holds for each argument. Either fi is affine, so if you have an affine argument, that's end of story, or h is increasing in argument I, and fi is convex. By the way, when you take k equals 1, this generalizes the rule that says, this will generalize the rule that says that an increasing convex function of a convex function is convex. Okay? And now we're just generalizing it to multi-arguments, and it's this. By the way, proving this is about 3 lines. In the completely general case, right? Not with all details. Yeah.
Can you quickly say what's the difference between an increasing convex function and a convex function?
Wait, can I say what the difference between an increasing convex function and a general convex? I can. A function that is not increasing doesn't always increase. Oh, no, sorry. I'm being informal here. When I say increasing, I mean non-decreasing. So, yeah, thanks for asking. Sorry, yeah. So by increasing, I'm being informal. Because they're slides. There are a few details that I'm not showing you here. They're not that complicated, but it just makes it more weird and pedantic for me to say non-increasing. And there's some weird things about the domains and stuff like that, which I'm not saying. Yeah, so don't think this is a slide. This to be interpreted as slides, not exactly math, but it's very close to math. It would only expand by a factor of 2, and it would be then it would become math, which is to say true. Okay, so yeah, so I'm glad you asked that question, thanks. Okay, so here it is. That's it. So it turns out this is everything. Let's see that. So let's start with this. I mean, this is kind of a silly way, but let's use this rule, this one rule, to show that if you double a convex function, it's convex. So how do you show that? So we're going to use a hammer to show something that's obvious. It's true. If a function is convex, then twice it is convex. So show me here. How do you do it?
Well, so the function
H?
will now be just take x times 2.
Yeah. So h is the function that doubles things. Okay?
So it will be convex, and
Yeah.
it will be increasing in the only argument it has, and we have a convex function.
Done. That's it. Okay? How about sum of 2 convex functions? How do you show it using this? You know the sum of 2 convex functions is convex. That's obvious, right? But let's show it using this. How do you do it? What's h? It's a sum function. I mean, it's stupid. It's just the sum. So this function, it's a linear function, which is, by the way, also convex, right? How about the max of two convex functions? You just take h to be the max function, but you knew that the max function is convex, and this is critical. The max function is increasing in slide talk, non-decreasing in mathematics, right? So, okay. So in fact, this one rule and its converse, not its converse, it's when you flip convex and concave, it's the only rule you need to know. There is no other rule. So as a matter of fact, you can be completely and utterly functional in basic convex optimization and convex analysis, I might add, if you simply know that one rule. That's it. Okay? It's not, I mean, it's not obvious, but it's true. And you have to know a set of atoms, about 10, 20 atoms, you're ready to go. Okay? So, okay. So that's pretty much the only rule you need to know. Right? So you can put it down on a little card and, in fact, and stick it in your wallet and take it with you everywhere. I mean, it's not, you know, okay. Everybody got this? Okay. So here's a function. God only knows where it would come up, but who knows? It's a function of two variables, right? It's u plus 1 log, u plus 1 over min uv. Now, I don't ask where something like that would come up, although you can imagine, right? Because if you're doing some kind of application and this is some Kullback-Leibler divergence and you make some other argument about this, that, and the other thing, and the next thing you know, you're looking at a function that looks like that, right? Because you're the first one ever to propose to do this kind of thing and blah, blah, blah. Okay? Everybody follow this, right? So, all right, so that function, that's convex. Okay, by the way, it's not obvious even remotely. Oh, of course, the first thing you always do, if it's just a function of two variables, is depends. You might just plot it, right? And just see if it curves upward, right? By the way, if you see that it sometimes doesn't curve upward, but sometimes, then what you do is you hide all evidence that you plotted it, and then you walk back out to your colleagues or peer, and you say, well, it's obviously not convex, like that. And they would say, well, how did you know that? And you go, oh, it's I mean, come on, are you serious? Just look at it. And then, so I recommend doing this, actually. You can do this, yeah. So, yeah. But if it does curve up on what you plotted, then now you show it. Okay, so let's show it. So this one is not obvious. This is not, I guarantee you I've done this. I've actually talked to people who do heavy-duty convex analysis. This just stopped. They can't do anything here, right? So, okay. All right, so let's take a look at this. So what we're going to do is we're going to walk from the leaves up to the root of the tree, of the parse tree. Okay? So here's how it's going to work. We're going to start with the leaves, which are going to be u plus u and v and 1. And now we're going to look at sub-expressions. So I'm using the language which is leading us to the next step. But, that's okay. So here's the way it's going to work. Well, u plus 1, that's an affine function because it's a variable plus a constant. And if you like, you could even imagine something like this. Constants are affine. Sum of two affine is affine, right? And by the way, if you really wanted to get fancy about it, you would say you didn't even have to tell anybody that the sum of affine is affine because affine means convex and concave. And if convex plus convex is convex and concave plus concave is concave, then affine plus affine is both convex and concave. Okay, I don't know if people followed that, but okay, that's fine. All right. So this sub-expression is affine. That's affine. Min of two variables. Actually, I could have had I could put a square root of u there just to make this even uglier. I mean, it doesn't matter, right? But so this thing is concave. Okay. And now the next one is we're going to look at the following function, x log x over y. That's like a negative relative entropy or something like that, right? Between x and y. That's small enough. That's in your atom list, so theoretically you've memorized it. I'm sure you did. So that's going to be convex. And that's small enough that you could actually take the Hessian, get a 2x2 matrix and verify it's positive semi-definite, right? So this function is convex in xy. And here's the critical part. It's decreasing in y. And here I really mean decreasing in math. So it's decreasing in y. Actually, no, because x could be 0. Okay, it's non-increasing in y. Okay? So if you increase y, this thing goes down, I mean roughly, right? So this is super interesting. That's a convex function, which is, what is its monotonicity in x? That's my first question for you. What? What is the monotonicity of that function in x? It's what? What does it look like? Plot it in your head. Is it? It's decreasing and then it's increasing. It's relative. It's negative entropy. It goes down and then it goes up. So here is its monotonicity in x. None. Right? It's neither increasing nor decreasing. Okay? So it has no monotonicity. What is the monotonicity in y? It's decreasing. Okay? So actually it's very interesting because you can go back to this single, there's only one rule. It's this. It says basically that if h is not known to be increasing or decreasing in an argument, the only way this rule is going to match is that the argument has to be affine. Yes?
There's something missing there. And
I don't think so, actually. It's possible because you're the first ones to see these slides, but I don't think so. But go ahead and try me.
you're defining a recursion, but you're not defining the base cases.
Oh, I have. I said we have atoms.
Sorry, so for example, the case of the 2 times x, then you said, how do you prove it's convex? And
Right, so all of this starts with a set of atoms. We're going to get to this. It starts with a set of atoms, a very small set. It could even be just the ones I showed you. That's the ones I showed you, which filled 2 slides. You don't need to know any more than that. That's already too much. So, yes, that's the base of the recursion.
Yeah.
Okay, so, all right. By the way, there have been a couple of typos. I think I pointed one out verbally. The other one I saw, but you didn't. That reflects badly on you, by the way. So I'm just going to put that out there. The next,
Maybe we just polite.
I don't believe it. I'm not going for it. Yes. You had a question? Yeah, you did. Sorry.
Next slide, you have x is actually u plus 1, right? So u plus 1 is always bigger than 1, so it's always, that's increasing.
Yes, that's true.
Yeah.
Yeah. But it's not relevant here. But you're quite right. That's right. Because this thing is actually, when x is bigger than 1, it's monotone. You're right. Right. So, but it's not relevant here.
But if y is big, that's not true.
If y is what?
If y is big, that's not true.
Ooh. I don't know. That's a good question. You're probably right. Why don't you two discuss it afterwards and then come tell me? But just to make it very clear, it's not relevant to this discussion. All we wanted to do was show that this hideous function here is convex, and we did. So, but you're right. There's more. Okay. Let's look at another example. How about log some exp here? That's a convex function of u's, and it's increasing. And now, I think somebody yesterday, someone from over there, I don't know if you sit in the same place, but someone asked me, oh, what if a function is random? So, it's random now. So, we're going to have a function. This is going to be the simple case. It's simple to go to you can go to the integral from this. But we're going to take a function which is now depends on a random variable. And for simplicity, we're going to have this random variable only take on a finite number of values, because you should always start with that case, right? So we start with that case. And in fact, we're going to start with the case where they're uniform, right? So there's values omega 1 up to omega k, and then probability 1 over k on each of those, right? So we're going to take that. And now what we're going to do is we're going to say, well, you know, if gamma is positive and these are convex, then each of these is a convex function. And so this is a convex function, and it's increasing in each argument. So that says that this function here is actually convex. By the way, if you want to, in your head, let k go to infinity or whatever, then you're going to actually find the moment generating function here. But that's another story, right? But I'm just saying this relates to things you've seen. Trust me. Okay? So that's convex. Because it's log of the expected value of e to the gamma f of x. Now, this function comes up a lot. And it comes up as a bound that goes, a very famous bound that goes something like this. By the way, completely elementary, very powerful. And it looks like this. It says that the log of the probability that this, so if this were a constraint, if your constraint were that this thing should be less than or equal to 0, this is the probability that you violate that constraint. So this says that the log of the probability that you violate the constraint is less than or equal to the log of this. Now, this thing actually is not a convex function of x, and this one is. And so it turns out, in fact, an extremely good method for handling problems where you have, well, it's called a chance constraint problem, where you say this constraint has to hold with probability 99%. An extremely good method is actually to use a surrogate, which is this convex function, right? So, okay. So somebody did ask yesterday, and here it is. Right. Actually, it turns out it's more than a surrogate. It turns out, like in many of these cases, it turns out that the original constraint is nonsense, and you shouldn't have asked it for it in the first place. Even if you think that's what you wanted, it was wrong. So I'll get to that later, maybe. Okay. Okay. So now we're going to get to the idea of constructive convexity verification, right? So you're going to start with a function given as an expression. I've been saying a lot of these things all along anyway, so it should be kind of obvious, right? So you start with a function given as an expression. You build a parse tree for the expression. The leaves are going to be variables or constants and parameters. The nodes are sub-expressions, so they're functions of the children, but each one has to match this general rule, okay? And you're going to tag each sub-expression as convex, concave, affine, or constant, right? So that's how you're going to. And a variation, which is actually fairly useful, is you walk the tree and you tag every sub-expression as positive, negative, this kind of thing. You can do fancier things, right? And if you do that, this allows you to say more about monotonicity. For example, the square function is not monotonic if you don't know the sign, but if I tell you that x is negative, then the square function is decreasing, and you're going to match more rules, okay? Now, of course, if you have, this is constructive convexity verification. So it says if I have an expression, and I write it this way, and I have a parse tree, and every node in the parse tree matches that one single rule, or that rule and its concave analog, then, of course, you know that function is convex or concave, right? Now that's sufficient, but it's not necessary. And that's actually not the point, right? So let's look at one. So here's one. You know, x minus y squared over 1 minus max xy. It would not be hard to make up a practical problem where something like that would come up. It would not be hard at all. Okay, so the leaves are x, y, and 1. They're affine. Max xy is convex, so this is convex. X minus y, that's a difference, that's going to be affine. Therefore, 1 minus max xy, that's concave. Then you have u squared over v, that's going to be convex. It's monotone decreasing in v. The domain is v positive. And therefore, the whole thing is convex, right? Because it's in the first argument, this is u squared over v with u equals x minus y, which is affine. And v is going to be 1 minus max xy, which is concave. To expand that, that's because minus max, max is convex, 1 minus max is concave. Okay? So that's it. So these things, here's a picture of it. This is a screenshot from, you should go to this. It's just a little thing written by a student at Stanford. And what it does is it'll take a function from a small library. I mean, you just look up the library of functions there. It's obvious things, and it'll actually do. So here's the full parse tree, and let me explain what's being shown here. On the right of every sub-expression here is shown the sign. Plus minus means we don't know the sign. Plus means it's non-negative. Minus means it's non-positive. The curvature is shown on the left. If it's affine, it's got a line here. If it's convex, it's got something going up. If it's concave, it's got something going down. Okay? And so this just shows you what this function is here. Actually, if you were going to do the homework, then later today you would go to this website and you'd play, and there's actually a quiz mode. So the quiz mode generates a random expression, and your job is to say it's convex, it's concave, or you can't say neither. The correct statement is it is not, it cannot be proved convex or concave from this general constructive convex analysis. Okay? So those are the rules. I'd recommend doing it. What?
So I might have missed that, but you said 1 minus max is convex, but isn't it actually an affine function
1 minus max of xy is concave. Let's go through that slowly. Right, so max is convex. Okay? Then we could use
Something is affine?
no, minus unary minus of a convex function is concave. So
I think that wasn't your basic rule.
my unary minus works fine. Go to the composition rule and take the outer function to be the very complicated function. H of u equals minus u. Okay? Now, that function is concave, right? And it's, let's see, and it's decreasing. Therefore, h of convex is concave. Done. So it does. Trust me. Okay, so here's another example, just for fun. It's a great example, and it'll actually make some of the stuff very, very clear. So here it is. So f of x equals square root of x1 plus x squared. Well, of course that's convex. It's the norm of the vector 1 comma x, right? Of course it's convex, right? So let's try to show it. Let's make the parse tree. Well, at the top you have square root, and you look for a rule that matches that. By the way, the only thing, if your top calling function is square root, the only thing it can conclude is that it's concave. We're trying to show convex, so we're end of story right there, right? But there's no rule for this, right? So this doesn't work. So this function, that's an example, or sorry, this, so whether or not you match this rule, whether or not you can be shown convex by this rules, that's called disciplined convex programming. We'll get to that in a minute. But so this is something that is convex but cannot be shown to be convex using constructive convex analysis. Okay? So, and let me make it very, very clear what the point of constructive convex analysis is. It is not to determine if a function is convex, right? It is to give you a set of tools that allows you to construct and show a subset of functions that are convex, very simple proofs that those functions are convex or concave. That's the point. Okay, so let's talk about disciplined convex programming. We've been talking about it for a while, but this is the idea. It's a way to describe convex optimization problems. It's not based on constructive convex. It is constructive convex analysis, right? It's a sufficient but not necessary for convexity, right? And it's the basis of a bunch of domain-specific languages. So here it is. By the way, those trained in undergrad computer science will know what this is. Essentially, I'm about to give a formal description of a grammar. Okay? So this is it. This is very close to like Backus-Naur form or something like that. So here it is. So a disciplined convex program has 0 or 1 objective, and it can have only 2 forms. It can either be minimize of a scalar convex expression or maximize a scalar convex expression. Concave, sorry. Right? So that's or nothing, right? Because it could have 0 objectives. Okay? That's it. It can have 0 or more constraints. If it has 0, that's called unconstrained, of course. But otherwise, it has can have more constraints. And each constraint, they can only be 3 types of constraints. They are affine equals affine, convex less than or equal to concave, or concave bigger than or equal to convex. That's it. Okay? So, by the way, this doesn't fit the exact original rule. The original thing was fi of x less than or equal to 0. But if I had convex is less than or equal to concave, I would rewrite this as convex minus concave less than or equal to 0, but minus concave is convex and the left-hand side is convex, okay? So, and this is more convenient, much more convenient to write it this way, okay? So that's it. Everybody got this? It's very simple. So you can write square of x is less than or equal to the min of z and 1. Did everybody get that? Or was it too fast? It was correct because the left-hand side was convex and the right-hand side was concave. You get quite good at this after you've done this for a while. Okay, not even a long while, right? So what are expressions? Well, an expression, these are formed from variables, constants and parameters, and functions from a library. That was the initialization of the recursion. Okay? The library functions, you have to give the known convexity, that's the curvature, so convex, concave, affine. You have to give monotonicity, if there is any, in each argument. And sign properties, right? That's pretty simple. The sign properties are basically, I mean, it's not that simple. It's close enough. It's just sign arithmetic. It's very simple. Okay. all sub-expressions match the general composition rule. So that is actually a formal definition of a language. And so this generates a language of expressions, right? A set of expressions which are going to be they're discipline convex program DCP expressions. Okay? So actually, how many people know what I'm talking about when I say it's a language and these are okay? Some. Good. Great. Good. I mean, there's not much more than what I'm saying. Oh, except I am saying this. This looks informal. This is not informal. This is exactly. And if you actually program in a real language, you would realize that some of the things I've written here, for example, this thing, in a real object-oriented language, you can imagine this. You can easily imagine that's 3 lines of code, maybe 3 to 5 lines of code, depending on the language. To actually, if you have a family, to implement the isDCP method. Between 3 to 5 lines in a real language, right? Because you simply ask, you ask yourself, are you convex or concave? You look up yourself and you ask about your attributes about monotonicity, and then you query each of your children. Done. So it's very shorter than the slide, the actual code, right? So, I mean, what should have been clear is that everything I've been talking about translates into a code very, very easily. And beautifully. Okay. So a valid discipline convex program, it's convex by construction, right? By the way, this is not what you might imagine, how you might have imagined you would do these things, right? You might have imagined, I mean, so here's what you might first imagine you would do. You would write down the problem you want to solve. And then some symbolic analysis tool will work on it for a while and come back half an hour later and say, great news, you have a convex problem, right? And these were the first things I worked on with my students, which is to say they worked on. Right? So, and one day somebody walked into my office, a student, and he said, watch this. And he wrote some horrendous expression on the board with arcsine and log and all sorts of crap. And he said, do you know that's convex? I'm like, how the hell would I know that? I don't know. And he goes, yeah. He said, we did it. And it was a very sophisticated thing. It did what you suggested. It did interval analysis and different parts called different things, and it got tightened and everything. And eventually, after something like 4,000 iterations going back and forth, it was able to establish that it was convex. And we looked at it and we said, that is so cool. And then there was a pause for a while. We both looked at each other and we said, that is so useless. So I had to counsel him for a little while after that because that was his dissertation. And it's a really good dissertation, actually. So, but actually what it is it tells you that's not what you want to do. Here's why it's useless, right? Because in fact, that whole thing supports a very bad way to do optimization, which is the monkey at the typewriter. Everybody knows about the monkey at the typewriter, right? So the wrong way to do it's convex optimization for sure, actually any optimization, is to just type in your problem. Oh, I want this and I want that. And then say, oh, well, I'll just go to lunch now while my symbolic analysis thing checks if it's convex. And you come back after lunch and say, it is. And you go, oh, that's great. But you have not a clue. You have no idea why it's convex. You change parameters, and it's not convex. Somebody says, no, we're gonna use the hinge loss model, not the logistic. Why? God only knows, right? And now it's not, and you don't know why, right? So turns out this is the right way to do it. Is a question. Sorry? Oh, okay. All right. Okay, good. Okay. All right. So this is the idea. Now, very interestingly, what this says is convexity depends only on the attributes of the library functions, not their meaning. So you can actually switch out square root and fourth root, right? Or exp and the non-negative part, because they have exactly the same attributes. In other words, for example, these two are both convex, they're increasing, and they're both non-negative. Done. Because that's all that matters in this, okay? So, okay. Now it turns out it's extremely easy to write a parser for this. I mean, in a very high-level language, you just say, make me a parser, here's the language, it's done. You don't do anything. You just say, parse it, and then you get it. So it turns out, this is something I'm not going to go into, but it would be shockingly short. It turns out once you have parsed one of these expressions, it's actually very easy to take that through transformations and make an equivalent cone program. I'm not going to tell you how that happens, but it's actually kind of interesting, but it's also not complicated. Very short amount of code, right? Then you have it. And what you have now is a modeling framework for convex optimization, right? And so I'm going to talk about those. So These are basically domain-specific languages for optimization, right? Yes?
One thing I'm missing is a way to reason about monotonicity, right? Because for this general
Yes.
rule you showed, you need to know also increasing or decreasing.
No, you don't. So it turns out we're only using monotonicity locally. So the only place we do is you take a sub-expression, so you ask who's the caller, and then you ask that caller what is your monotonicity in each of your parameters. Is there, oh, sorry. I was missing the hand signal. That was the universal hand signal for please repeat the question. So, okay, I got it now. I'm sorry. Okay. Okay, so the question is, how do you reason about monotonicity? You can reason about monotonicity, but actually we don't do it, and actually you don't need to for this. Because you only check, monotonicity only applies locally for each atom.
But any like sub-expression might be an atom for some other sub-expression.
No. Atom is a fixed library. It's an absolutely fixed library. It's got 30 functions in it. And you know most of them. Some, scalar times it, quadratic, norm, x squared over y, log sum x, that's it. Yeah, so I know what you're saying, but actually it turns out if you go back and look at this, we don't reason about monotonicity in the basic variables. We only look at monotonicity with respect to your children. So, I'll tell you about this later. That's it. With respect to that's exactly it. So we are only using monotonicity with respect to the arguments of each function. That's exactly the right way to say it, right? But you could reason about monotonicity all the way from the children to the top. That you could do too. It's not hard, right? To make a set of sufficient conditions that an expression is monotone, increasing or decreasing in a given variable. We could do that too. That's not too hard. Sufficient, not necessary, right? Okay. So the idea in one of these things is you're going to declare variables, you're going to form constraints and objective using the kind of rules I've been talking about, and then you're going to solve. Now this is very old. These go back to the 70s, so this is like something like a math programming language. And by the way, it's not bad. This is written by one of the writers, the computer science guy on this, was Kernighan from C. So somebody who knew a lot about these things. Now, these classical things, in addition to being like basically commercial things, right, and not open, they don't care about convexity. They don't even know about convexity. So there's nothing there. And they're a bit weird. I mean, it basically fits the way people in OR think about optimization, right? Okay. So I'll mention a couple of these things. There's a whole bunch of them, and there's some precursors as well. There's YALMEP. Here was one of the first sort of object-oriented ones. CVX is one that's in MATLAB, unfortunately, but it's fine. More recent ones would be CVXPy or in Julia convex.jl, right? So these are that. If you're interested what this is, that's yet another LMI, which is linear matrix inequality parser, because these two are both linear matrix inequality or semi-definite programming parsers. And so this is a reference to YAC, if you know what that is. Actually, how many people know what YAC is? All right, good. You do.
There will be a question coming over the speakers.
Sorry, what's that?
Over the speakers, there will be a question.
Okay.
Just wait a second.
Okay.
Okay. So the question is, maybe I missed it, but as you said, there are functions that you cannot represent analytically. So how do you check convexity for those functions?
It's a good question. Well, let's see. It depends. This is a set of rules. If you have an atom library and you have some rules, actually, I should add, you have one rule and you have a set of atoms. And all I'm saying is you can generate a very large number of convex or concave functions from that small set. If you have some random one that just came up, you can try to express it in this form, and that's fine, right? So if you can't, then this doesn't say anything. Could be convex, could be concave. Okay, I'm going to move on. And I'll just give you a glimpse of what these things look like. So CVX, I think you saw a part of it before, but it would look something like this. This is in MATLAB, so it's MATLAB-ish, whatever that is. I think that's how you'd say it. And so it looks like this. You have two commands, CVX begin and CVX end. You declare variables, and so between here and here, x is actually an object. It's a variable object. If you ask what's x in there, it would say x is an affine expression. Okay? When it finishes, it verifies that all of these match the rules, right? That's actually very mechanical to do. And if it reaches here, and in fact you have a valid problem, then that's transformed to a cone program, and then that's solved, right? We don't have time, but I would normally ask you I'd ask you to ask me, how do we solve the cone program? But we don't have time, so, okay, we'll move on. So the idea, so this is what CVX, and it's kind of MATLAB-ish, it looks like. I mean, it's extremely readable, right? I don't have to write down what the problem is that's being solved here, right? It's completely obvious, right? So, okay. Here are some functions in the CVX library. You can have like norm xp. Here are some of its attributes. Here, pos of x is x plus, right? So it's the positive part. Square is this thing. In pos is this thing. Max, you have quad over ln, that's x squared over y. Here's lambda max of x. You know, so these are kind of obvious, right? But there's not many others, right? There's maybe another 10 or 20 atoms, right? Some of the atoms no one ever uses, they're just to kind of brag, right? Like the sum of the k largest entries, right? Yeah, that actually comes up every now and then in some obscure application, but yeah, it's just there mostly to brag. So here's how it works. Suppose you make a mistake. Suppose you write square root x plus 1 is less than square root y. That's recognized as convex. That's concave. This is cool, this one. So this is convex less than concave. That's fine, right? I mean, the next step before canonicalizing would be convex minus concave less than 0, but okay. Then you write max of xy equals 1, and you've made an error. You've made an error. Why? Because between equals, you can only have the only thing that matches that correctly is affine equals affine. That's the only thing. This is affine, and that is not affine. So you get thrown an error. And the error would come back and say this. Discipline convex programming error, you can't have convex equals real constant. Okay? So this is what that would look like. So, okay. CVX pi is in Python. And there it's very interesting because the variables and expressions, they live outside of problems. This is actually extremely interesting. So they live outside problems. And so you'd say x is a variable. That's a constructor for an object, a variable object. That's x. This is an expression. So you overload expression, you overload plus and various other things for expressions, right? And not only that, actually, I mean, the Python is like very short. If you followed anything else and you program in any real language, you could guess the things I'm talking about. The code fits on a slide. It's very, very short. This is a constructor for a problem. It says, make me a problem. And the constructor for a problem has two arguments, either one of which could be empty, right? So one is an objective. This is actually a constructor to make an objective. You can either say minimize cost or maximize, whatever, something else. Maximize argument. If it's minimized, the argument must be convex, or I should say must be DCP convex, right? And if it's maximized, it must be DCP concave. So this forms the problem, and then you call the solve method on the problem, and you get the solution. This has what this does is this goes back, and as a side effect, it writes on the object, all the objects which are the variables, it writes a dot value field if it was feasible. Okay? So that's how that works. Okay. So here you can do signed DCP, right? So for example, you would have abs of x is convex, it's non-decreasing and it's non-increasing and so on, right? So, and that allows you to match things. The way you would check, here was our example before, and if you wanted to check that, you would simply form this expression. You would simply write x is a variable, y is a variable, you'd form that's an expression. And then you would actually say expression.curvature, and then if you're doing this in interactive mode, it will simply type back convex, right? If you say expression.sign, it'll come back and say it's positive, meaning it's non-negative, right? And then if you say expression, if you call the .isDCP method, it'll come back and say true. Okay? So everybody got this? This is what this looks like. It's very straightforward. Now, in CVX-pi, you actually have parameters, right? Which is actually very close to what theoretically and mathematically a problem is, right? Because when you have an optimization problem, well, okay, what's the best algorithm to solve a single optimization problem? Convex or non-convex? What's the best algorithm? There is an absolutely best algorithm to solve a single instance of any optimization problem. What is it?
Answer.
That's it. It's return, left paren, answer, right paren. Everybody got that? Right. So the point is that makes no sense, right? So if you think mathematically about what is a problem is really a problem class, and it's instantiated by parameters in the class. So you'd say, here's my problem class, linear programming, or lasso, or SVM. You instantiate it with data. That's an instance from the class, and an algorithm is something that takes an instance and maps it to a solution, right? So this is actually much closer to the fundamental mathematics of what a problem really is. So, for example, if you wanted to do a for loop style trade-off curve, you'd do this. You make an empty array of values. That's going to store the values in your trade-off curve. And then you would just make a for loop that says this generates, well, like the people here know NumPy and things like that. I mean, you can guess what this is, right? This takes 100, it generates 100 numbers between 10 to the minus 4 and 10 to the 2, uniformly spaced logarithmically, right? Then what you do is you assign the gamma, that's a parameter, gamma.value equals val. And then you call the solve method, right? And then you would simply append the solution onto your list of values, right? Here's what's cool. I mean, this is an advantage of doing this in Python is now, unlike MATLAB, this is real, right? So now it's actually this simple to do the entire thing in parallel, right? So you simply import from the multiprocessing package, you import pool. Then you make a little function that does nothing more than this. You pass the gamma value, and it solves that problem with that specific gamma value. I mean, it's completely clear, right? And then you do this. You construct yourself a pool object with n processes, and then you do you simply map this. You apply this function, which is what map means. You apply this function to everything in this list, except you do it in parallel, right? So that's what this does. So that's essentially it. I mean, there is nothing more, right? And this is full on. Now you're doing multi-processing stuff. So that's how that works. Okay. So that's the advantage of it, right? There's also a Julia package, and it looks. Oh, I should say that this is. The point about CVX-pi is it's approximately Pythonic, which is the adjective you use to mean that the class hierarchies and the way things work look like kind of high fancy Python type things, right? So, okay. There's one in Julia. Actually, how many people have played with Julia so far? Okay, good. A bunch. So Julia is very cool. More of you should. Yeah, by the way, especially if you were accidentally in one of those fields where you were fed MATLAB as a child. I was one. I wasn't a child. So, but anyway. If you're from one of those fields, and you should know by now that you should wean yourself off this. You should know this if you're from one of those fields. This is a really good way to do it, Julia. It's, well, okay, we'll just say it's a good way to do it. So, all right. And everything looks the same, right? You form variables, you form costs. This constructs a problem. This says, use the solve function on the problem. The exclamation point means that it's going to have side effects, right? You don't have an exclamation point if it doesn't have side effects. So, and the side effect is to write onto the value attribute of all your variables, the solution, right? So that's it. Okay. So I'll just conclude. There's not much to say. So the idea is you have this constructive convex analysis. It is not meant to identify every convex function as convex. That's not the point. Never was, never will be. That's not what it's for. What it is, it's a way to show that a giant pile of convex and concave functions that come up in applications, like a giant pile, like I don't know of any function that doesn't come up this way, kind of thing. I do know a few, but okay. It's to certify those. So it's just an approach to doing this. It's very simple. It's, of course, sufficient. It's not necessary. And it's the basis of a bunch of modeling frameworks, right? And modeling frameworks are cool because they make rapid prototyping of convex optimization very easy. Now, when you couple one of these systems with the parser and everything, and then you call a generic solver, you could ask, is it fast? And the answer is no. Compared to a custom thing for that problem, of course it's not. Generally, the cost it's much less inefficient than you would imagine. It could be 2x inefficient. It could be 10x inefficient. But if you compare writing for 3 weeks a bunch of C++ to writing down a script that's 6 lines in 20 seconds, you know, it's clear the trade-off is kind of clear, right? So, okay, so we had people ask about this. By the way, this one I actually would do, if you were going to learn anything, you would want to look at some of these things. You should go to DCP and run the quiz just for fun. That'd be the minimum you could do. If you actually went and did the homework last night, which was to install one of these things at least, and Hello World in it, you now know what you're doing because they're all based on DCP, every single one. And so you should be, this is all new. We did a lot of math today, but it'll take a while to sink in. If you practice with this, you'll be fine by tomorrow. Okay, so we're gonna quit here today.